From the top, our goal is to connect to OCI from our local machine and manage infrastructure. The tool we're likely familiar with for that is the console, but it's important that we dig a little deeper. Under the hood, every interaction with OCI is through a REST API endpoint. So, for example, whenever we want to create a VCN, we have to hit the endpoint with a request that looks something like this. Obviously, working with the API directly is rather unwieldy. Writing these comes up in specific use cases, like in application integration, but more often than not, it's easier to work with high-level tools that generate these calls for you. The important thing is to be loosely familiar with the API, for two main reasons. First, permissions are granted at approximately the API level. So, to implement the principle of least privilege, we need to understand which API calls we grant to each actor. Second, when things go wrong, figuring out exactly which API call failed is often a great first step in debugging. But, for the most part, we'll generate these calls through other tools. The first and most familiar way is with the Cloud Console. This is the web application where you can click around to manage your environments. It's the easiest tool to use and is great for prototyping or for small environments, but when it comes to more complicated actions, like, say, provisioning 100 compute instances, it becomes labor-intensive and error-prone. The appropriate tool for automating repetitive tasks is the Command Line Interface, or CLI. This is a simple text-based utility that can be installed on most operating systems' terminals, including macOS, Windows, and Linux and Unix-like systems. This way, we can leverage shell scripts to manage infrastructure. If we want to provision 100 compute instances, we could write a quick bash script that loops 100 times. Or, for example, if we wanted to change the shape of every compute instance in a compartment, we could write a script that queries for all of the compute instances and then iterates over them, changing their shape. But, just like the console, when use cases get even more complex, the CLI can also become unwieldy. Suppose we want to automatically provision a new server and decommission an old one if certain health checks fail. Or, suppose we want a pilot-light DR environment that automatically replicates prod, but scaled down. For these, the appropriate tool would be the SDK. The Software Development Kit, abbreviated SDK, consists of libraries for various programming languages that will generate API calls for you. This way, we can leverage the full generality of languages like Python, Ruby, or Go, just to name a few. As opposed to the CLI, the SDK becomes the most natural tool when complex logic is involved. Additionally, the SDK can be used for serverless functions that are executed based on custom API calls or infrastructure-emitted events. Just to show a quick example, here's a Python script that creates a VCN. It loads settings, establishes a connection to OCI, packages up details for the VCN, then sends the request to OCI. Summing up, we have that OCI is fundamentally REST API based, but we generally use higher level tools to generate those calls. The console is best for simple use cases, experimenting and prototyping. The CLI is best for simple but repetitive tasks and automation. And the SDK is best for complex automation. Throughout this course, we'll stick mostly with the console and the CLI, and two other methods we haven't mentioned yet. But it'll be helpful to keep the API in the back of your mind as a way of unifying the different methods. In the next few videos, we'll go into a little more detail on the CLI, starting with the authentication methods. See you there. Before you can actually do anything in the OCI CLI, you'll have to set up authentication that lets OCI know who you are. So in this video, we'll go over the different methods of CLI authentication. Recall that all interaction with OCI is through a REST endpoint, and that all the CLI does is generate and sends requests to that endpoint. But before the endpoint passes that request on to any other service, it asks the Identity and Access Management Service to verify that you are who you say you are, also known as authentication, and that you are allowed to perform the action that you're requesting, also known as authorization. To facilitate this, your CLI client attaches some sort of identification to its API requests. Just to get a little more concrete, in the API call example we showed earlier for creating a VCN, that just means adding some headers right here, that function kind of like a username and password. But again, knowing the details of the API isn't that important. In any case, the two types of identification that we'll be going over are API keys and security tokens. API keys are the easier but less secure method. To use one, you generate it in OCI, usually through the console, download it onto your machine, and then point your CLI to it. Then, your CLI can attach it to all of the API requests it makes. There are two main reasons it's not particularly secure. First, the key does not automatically expire. It's valid until you specifically deactivate it with OCI. Second, the key isn't bound to any particular machine, so any machine that has the key can authenticate with it. While API keys are nice for use cases that don't require tight security, we generally recommend the other method, security tokens. To use a security token, you first tell your CLI that you want to use one. Then, it sends a request to OCI, which in turn redirects you to a browser where you can sign in. Then, OCI gives your machine a session-based token that automatically expires after an hour unless refreshed. During this session, your CLI can attach the token to your API requests, authenticating as you. So, while you do have to sign in every time that you sit down to use the CLI, security tokens are much more secure than API tokens. So far, we've talked about using the CLI from local machines, but you can also use the CLI from machines within OCI, like compute instances and functions. Because these machines have OCI managed metadata, like OCIDs, instead of authenticating as you, they can just attach their own identities. For compute instances, this is called instance principal authentication. And for functions, it's called resource principal authentication. Of course, just authentication isn't enough, so there have to be policies within OCI that authorize these principles. But we'll talk about that in a later module. The last thing I'll mention is the Cloud Shell. The Cloud Shell is a web application within the Cloud Console that streamlines CLI usage. It works by automatically provisioning a small compute instance with pre-configured security tokens and connects to it through your browser. Then, the CLI client itself runs from the compute instance so it can attach its security tokens to your API requests. For the most part, this is where we'll be doing all of our CLI work. And that's it. So we have that the two basic ways of authenticating from the CLI are API keys and security tokens. Machines within OCI can use their metadata for instance principal and resource principal authentication. And finally, the Cloud Shell is a mini app within the Cloud Console that connects you to an OCI managed VM with pre-configured security tokens. Next up, we'll take a look at some of these in action and then begin discussing the basic syntax of CLI commands. See you there. In this video, we're going to demonstrate installing the OCI CLI and then using either API key-based or token-based authentication. Since I'm on a Mac, we'll start by updating Homebrew. This will vary based on your operating system, but for the most part, you can just use your default package manager. Now, I can just use Homebrew to install the CLI. OCI's documentation goes over this for each supported operating system. Alright, now that we have the CLI installed, let's set up an API key. To do this, we can run OCI setup config. It'll ask us where to save the config file. We'll just hit enter for the default. Then, it'll ask us for our user OCID. I'll grab mine from the console. Then, it'll ask for our tenancy OCID. I'll grab that from the console as well. Then, we select a region. I'll put 40 for Phoenix. It'll ask whether to generate a new API key, and I'll say yes. And it'll ask where to put the key, what to name it, and what passphrase to hide it behind. Now that we've generated an API key, let's go to the console to upload it to our user. We'll select Add API Key, choose Public Key File, and select the key we just created. When we click Add, it generates a config file and fingerprint for us. The OCI setup config command that we ran already set this up. But if we started by generating a key from the console, we could then copy and paste this into a file manually. Now, let's head back to terminal to test the key out. First, if we check the .oci directory, we can see it has a config file and an API key. If we cat the config file, we can see it points to our user, tenancy, and key. Whenever we run an OCI CLI command, it'll check this file for this information. Let's verify that it works. We'll use OCI, compute, instance, list to list the compute instances in a compartment. Let's throw on the -h option to see what parameters are required. Here, we can see that the only required parameter is the compartment OCID. Now, we'll pass the command to compartment OCID. We could execute this command as is, but it'll actually return a lot of information. To simplify it, just for this demonstration, I'm going to use a slightly more advanced option and query specifically for display names. And now, we can see that I have one instance named example instance. Next, let's take a look at running the same command using token-based authentication instead. To do that, we'll start by running OCI session authenticate. It'll open up a browser where I can just sign in. Now, it'll ask for a profile name. I'll say example token. Now, we'll type in our command as before. The difference here is we'll specify our profile name and that we want to use a security token. And you can see that we get the same results as before. So there you have it. We installed the OCI CLI, then used both API key and security token-based authentication. In the next few videos, we'll go over the basic syntax for CLI usage. See you there. You have to tell it what service you want to talk to. For example, you could choose compute, network, or database, to name just a few. To figure out what keyword to use for which service, you'll have to either look at the documentation or use the command OCI-H. Once you specify the service, you need to tell it what resource type you want to interact with. For compute, an example would be instance. For network, an example would be VCN. And for DB, an example would be database. For each service, you can again use the -h option to view the possible resource types. Then, you have to specify the action you want to execute for that resource type. Some examples that are common among different resource types are create, delete, and list. Just like before, we can get the reference for each resource with the -h option. And finally, each command takes a list of options, some mandatory and some optional. These will vary widely between different resources and actions, but again, you can use the -h option for help here. We'll talk more about options in a second, but let's walk through a concrete example first. Starting from the left, we have OCI as the base command, as always. Then, we're selecting object storage as the service. The fact that it's abbreviated as OS is just something you'll have to use the reference for. Then, we select bucket as our resource type within object storage. And finally, we say that we want to create one. If we use the help option, we get an output that looks something like this. You can usually scroll through these documents with the arrow keys. If we look at the required parameters, we can see that we have two required parameters, compartment ID and name. For us to specify those, and an optional parameter looks a little bit like this. We give the namespace, the bucket name, and the compartment OCID. To figure out how to do this in general, let's look back at the CLI help command. If we look at any of these parameters, we'll see that it gives a type for the option. In this example, all of them have text. Let's dig into these a little bit. Options have four basic types. The first is text. This is just a string of characters. The gotchas here are to use quotes if there are spaces, and to escape any special characters based on the shell. Second, we have integers. That just means a number. Third, we have Booleans. For these, you have to just enter true or false. And the last and most difficult one is complex type. These are JSON strings. In general, you'll have to generate a JSON template to fill in to figure these out. To do this for a single parameter, we can use the generate param JSON input option and pass it the parameter name. An example output of this would look like this. Here, we can see how to format the JSON for CIDR blocks of a VCN. Each string would specify a single CIDR block. If, instead of generating the template for a single parameter, we wanted to generate the template for all parameters, we could use the parameter generate full command JSON input. An example of that would look like this. Here, we get a template that we can fill in for any of the possible parameters for generating a VCN. Just to show a couple of examples of complex types, this first example uses a JSON string to specify the CIDR blocks of a new VCN. This second example uses a JSON string to specify key value pairs for metadata while uploading a file to object storage. And that's most of what you need to know to use the OCI CLI. In the next video, we'll take a look at some of these commands in action. See you there. In the last video, we went over the fundamentals of the OCI CLI. In this video, we'll work through a couple of examples of writing CLI commands. We'll start by provisioning a subnet in this VCN. Let's open up the Cloud Shell so we don't have to worry about installation or authentication. We can open up the CLI in interactive mode with OCI-I. Now we can use its auto-completion to fill in network, subnet, create. And you can see that it lists all the parameters and highlights the required ones in red. Let's start with CIDR block and fill in 10.0.2.0/24. Now let's fill in compartment ID. It'll be blurred in the video, but the dropdown shows the display names of all of the compartments in the tenancy, and it'll fill in the corresponding OCID that we select. Now we can do the same for VCN ID. Let's also add an optional parameter for display name. Let's name it example subnet. And let's hit enter. And now we'll see a new subnet pop up titled example subnet. And there we go. Now, while interactive mode is great and does a lot of work for us, it can't quite help us out for parameters that take complex types. So to work through an example of that, let's provision an ARM compute instance. Let's start by running OCI compute instance launch and -h to see the required parameters. We can see that we need the availability domain, compartment OCID, shape, and subnet ID. Compartment OCID and subnet OCID are fairly straightforward, but we'll need to figure out what to put for availability domain and shape. As you'd expect, you can refer to each AD of a region with a name. For example, Phoenix has PHX-AD-1 and PHX-AD-2, etc. But in order to distribute load across the ADs, OCI assigns a prefix to these names that will vary by tenancy. That way, your AD1 might be different from my AD1. To see what my AD names are, we'll query the IAM service with OCI, IAM, availability domain, list. Now we can see the names of my ADs as well as their OCIDs. Now let's figure out what to put for the shape of the compute instance. To do this, we can query the compute service for the available shapes with OCI, compute, shape, list, and let's pass it a compartment ID. But if we scroll through this, we could see that it returns a lot more than just the names. For each shape, it also gives all of the metadata around it. Just so we don't have to sift for names specifically, I'm going to run the command again, but with a filter for the shape name and description. I'll do that with query, and then data, dot shape, processor description. These queries use the James Path language, spelled J-M-E-S path, but that's a little out of the scope for this video. For now, you can just note this down and paste it for whenever you need. And while I'm at it, let's format the output as a table. And pipe it into less. And now we can see our choice down at the bottom, vmstandard.a1.flex. Now let's fill in all of the required parameters and try launching this instance. OCI, compute, instance, launch, availability, domain, the string we noted earlier, and we'll pass it a compartment OCID. We'll specify the shape name we just chose, and let's give it a subnet ID. And let's go ahead and run that. And we see that it didn't work. This is because in addition to the individually required parameters, sometimes there are sets of optional parameters from which at least one must be specified. In this case, we have to either specify an image or a boot volume, which makes sense if we think about provisioning from the console. Let's specify an image. To get the OCIDs of images, we can query the compute service with OCI, compute, image, list, and we'll pass it a compartment. And we can filter by a chosen shape with shape, vm.standard. Of images, we can query the compute service with OCI, compute, image, list, and we'll pass it a compartment. And we can filter by a chosen shape with shape, vm.standard.a1.flex. And just so we can scroll through it, let's pipe it into less. Like with shapes, it returns a lot more than we really want to look at right now. So I'll rerun it, but with a filter for just the display name and the OCID. And let's output it as a table. Great, so we can note any of these down. I'll choose the latest Ubuntu image and retry our command. Image ID, and paste that in. And it doesn't work again. This is because we specified a flex shape, but it doesn't really make sense to specify a flex shape without also specifying OCPUs and memory size. So let's figure out how to use the shape config parameter with OCI, compute, instance, launch, and then generate, param, JSON, input, shape config. And we get a little template that we can fill in. For ARM flex shapes, baseline OCPU utilization and NVMEs don't really make sense, so we'll omit that. So, for the last time, let's fill in our command and add shape config and then a JSON string saying memory in GBs. We'll say 16 and OCPUs, and we'll say 1. And if we minimize this, we'll see a new instance pop up. Obviously, that was way harder than just going through the console and provisioning one. But in scenarios where we want to provision hundreds or even just tens of these, the CLI will save us a lot of time, especially after we get comfortable with it.